Hi, in this Unity URP shader tutorial, we're going to create a blur shader like this. This is a material that can be added onto a quad, so it can be used anywhere, not a post-process effect. This will be done by a box blur implemented with a convolution in the fragment shader. We'll be able to change the size of the convolution, which will make it blur more, but be more expensive. Additionally, implement an offset to get more blurring at less computational cost, meaning you can use the right combination to suit your performance needs. Let's get started. For this, I've started with the standard Universal 3D Unity URP project in Unity 6.2. To make things a little more interesting, rather than using a few primitive shapes, I've added in a few models. These are all from Kenny.nl, one of several game asset designers who release assets on a free or donation model into the public domain, which is really cool and helpful when you're prototyping stuff. Then I just have a quad here off to the right, which we'll want to add the blur to. For now, I'll just drag it to the right half of the screen, so we'll be able to see the difference between blurred and normal. The first thing we want to do is add a shader. Right-click, create, shader, URP unlit shader. We'll call this box blur, as that's what we'll implement in a moment. Then we can right-click, create, material. We'll also call this box blur. In the shader picker on the material, we can select our new shader, which will be under Custom Box Blur. Let's drag that shader onto the quad. Nothing much has changed yet. The scene is a little brighter as my quad is no longer casting a shadow. Let's quickly talk about how the box blur is calculated and how we'll do this in our scene. A box blur is a convolution filter. What this means is that to calculate a pixel value, you calculate it based on all the surrounding pixels, and you can make this grid as big as you like. This will be one of our parameters. The question is, what proportion of each of the surrounding pixels do you take? There are lots of setups that get different results. For example, we use this process in my edge detection video to detect horizontal and vertical lines. For the box blur though, it's very simple. As we're blurring the image, all we need to do is average the surrounding pixels, and this will average out our image, which has the effect of blurring it. So each pixel has weight 1, and then we divide by 9 if it's a 3x3 grid, as that's how many pixels we took into account. You need to do this normalization step, so we keep the same brightness in the image. This is what we're going to do in our shader. However, in your fragment shader, you're calculating the output a pixel at a time. How are we going to get the surrounding pixel values? Luckily, URP has some help for us here. Back in Unity, if we navigate to the settings directory and choose the PC RP asset, this contains the URP asset settings for the PC, which I'm obviously using at the moment. Here at the top, you can see there is opaque texture, and ensure that this is checked. It is on by default for me. What this means is the pipeline will render out all the opaque objects to a texture before doing the rest of the pipeline. So if your blur shader is in the transparent queue, which comes after the opaque, we can use this texture to get the surrounding pixels. As it says in the tooltip here, this will be available as _CameraOpaqueTexture. That's everything we need to know. Let's dive into the code and see what we can do. At the top of the shader, we have the name and path. As we have already seen, it by default puts it in the custom folder and names it as you named the file. All is good there, we don't need to change anything. The default properties come with a base color and texture. We don't need either of those, so we can delete both. Instead, we'll add two new properties. The first we'll call _blur. This is going to be our blur strength. We'll use this to modify the size of the convolution filter. As such, its type is an integer. We'll default it to 1, which will end up being the smallest size of filter we do, a 3x3. The second property is going to be called _scale. The convolution filter can do any blur amount by increasing the size, but the bigger it is, the more expensive it is to compute. So our _scale property is going to give us more blurring without increasing the performance cost. We'll do this by increasing how far we look for each texel we're going to compare in our blur. We'll limit this within a range between 1 and 5, because if you go too big, it starts to look weird. Again, we'll default it to 1. In the subshader, we need to update the tags. By default, the shader is opaque. You may think a blur needs to be transparent, but actually we'll be creating an opaque object based on the things behind it, so it can stay opaque. However, we want it to be processed after all the other opaque objects, so it will need to be added to the transparent queue. So we update the render type to set the queue as transparent. The attributes struct is the data we pass into our vertex shader. This is the position in object space and the UV. We're not using any sort of texture, so we can remove the UV from this. The varyings are the output of the vertex shader that go into our fragment shader. In this one, again we have a UV which we can remove. However, this time we'll replace it with something else. This will be a float 4 called screen pos, which we'll use the text coord 0. This is going to store where on our screen the vertex maps to. We're going to use this in the fragment shader to choose the pixels corresponding to this point from the opaque texture we referred to earlier. The next two bits of the shader define the texture 2D and the sampler. We've already removed _basemap from our properties, so again let's delete these and start again. The texture 2D we'll use is the _CameraOpaqueTexture. This is the texture with all the opaque objects rendered to it, and the sampler will be the associated sampler, which is called sampler_CameraOpaqueTexture. This will make it so we can sample pictures from this texture, which is what we need to do the blurring. Finally, before creating the vertex and fragment shaders, we have one last bit of setup in the shader. This is the cbuffer_start section. This holds references to the properties that you want for each instance of the material. We've removed those two properties, so let's clear them out. Then we simply add in the two we added. These are an int called blur and a float called shade. The vertex shader is very similar to the original, but I'll start from a clean slate for them both and go through it all. For the vertex, we define a varyings out struct to be our object, which will return, which gets passed to the fragment shader. In this, the first thing we need to do is add the position HCS variable. This is done via the transform object to hclip function, passing in position OS from the in input. This is the same as the stock shader. This is just moving our vertex position from object space to homogeneous clip space. The next line is different here. We populate our new variable screen pos. There exists a helper function, compute screen pos, for us. As expected, that takes a position in clip space that we've just calculated and calculates the screen space position. This is great because then we can use that to reference our opaque texture later. That's all the bits done here, so we just return the newly constructed out object. The fragment shader is where all the heavy lifting happens. The first thing we want is a float 4 out, which will start at 0. This is going to be our pixel colour, which will accumulate from the convolution, which is why it starts at 0. It's a float 4 even though we're returning a half 4, because if we're summing up lots of pixel values, we can easily blow through the precision of half 4. We'll convert this back to a half 4 at the end once we've normalised it and it can fit in again. To get our position that we use to sample from our _CameraOpaqueTexture, we need to do the perspective divide. Define a half 2 pos, which is in.screenpos.xy divided by in.screenpos.w. This will correctly map our screen position to a texture coordinate. The next thing we need to know is how big each texel is. That is how far along our CameraOpaqueTexture we need to move for each pixel we want to average in our box blur. So we have a half 2 texel. The size will be 1 divided by _screenparams.xy. This gets you the size of a normal texel. And then we multiply this up by our _scale property. So if a texel was 0.1 and scale was 2, then we'd essentially skip a texel when doing our convolution. The _blur property is just defined as an int. I don't believe you can use a range like we did for the float, so we just need to put in some bounds on this to ensure it's at least 1. Because having a convolution that's negative in size doesn't make any sense. So we'll define an int blur size. If _blur is greater than 0, then we just pass it through, else we set it to 1. Here we've used the ternary operator rather than writing out an if statement. These are better for GPUs, please look them up if you've not seen them before. Now for the convolution. For this, we simply iterate over the square of pixels we want to average. So we'll use a double for loop here. The first takes an int I from minus blur size to blur size. Note the less than or equal. If blur size is 1, then this would be -1, 0, 1. Then the inner loop is the same for an int called j. Together, these are going to be the offset into the texture. We sum into out the value given by sample texture 2D. The first parameter is our texture, so CameraOpaqueTexture. The second is our sampler, sampler_CameraOpaqueTexture. Then finally the location we want to sample. This will be our pos, which is our center point. Then to this, we need to add on our offset. This will be a 2D point, so we create a new half 2 with I and j to do that. And make sure we multiply this by our texel size so we get the correct floating point offset. Once that loop has been done, we'll have summed up loads of values. We need to normalize these so they're back in the expected range. As we're doing an average, we simply need to divide out by the number of points we accumulated. I've simply put here the formula for the number of points, which is 2 times blur size plus 1 squared. So for blur size equals 1, that's 3 times 3, blur size equals 2 would be 5 times 5. We shouldn't be calculating this within the fragment shader, it's essentially a constant. So that's wasted compute, but for simplicity I've left it in. The other way to do this would be to calculate it in the C# script, pass it in, and that felt like overkill for this short tutorial. Anyway, now we've got our out normalized, the values in that float 4 will be small again. When we return, there is no issue casting this down to a half 4 like the shader expects. We pass in out.rgb for the first 3 values and hardcode the alpha as 1. We don't want any transparency on our object. That's it, all done. Back in Unity, we can see our blurred quad looks like it has gone transparent. But indeed, if you look closely, you should start seeing some blurring. Let's just open up the material and we can see what adjusting some of the settings looks like. Firstly, we'll increase the blur strength, i.e. the size of the convolution filter. If I up it to 10, you can see there's some serious blurring going on there now. If we put this down to 3, so it's doing less work, you can see that the blurring is much more subtle. Now let's see if the scale parameter to offset the texels does indeed get us more blurring without increasing the size of the filter. You can see as I increase it, in the slider we're getting more and more blurry. Great! I think a strength of 3 and a scale of 3 is about equivalent to a strength of 10, so that's working really well. Have a play around and see what you think looks good. If we select our quad now, we can move it around and you can see it's working in real time as you expect. What's nice is you can move your quad back in the Z direction so we can blur parts of things. You wouldn't be able to do this with a post-process blur that just goes on top of the image. And that's it. I hope you found this tutorial useful in some way. As ever, the full code is on GitHub and linked in the description below. See you next time.